In this segment, we're going to talk about luminosity and flux. Luminosity is the total amount of energy radiated in 1 second and is given the letter L for luminosity. So luminosity is energy per unit time. Typical energy units are joules, and typical time units are seconds, which is a joule per second, which is more commonly known as a watt. So luminosity is power, and units of power are watts. An analogy is a light bulb. So let's say you went to the store and bought a light bulb, and it had a rating of 40 watts. Well, the power output from the surface of the light bulb is called luminosity, and that luminosity is 40 watts, which means it's going to send out a total amount of energy of 40 joules in 1 second. Let's say instead you went and bought a 100 watt light bulb. Well, that's the power output at the surface of the light bulb of 100 watts, which is 100 total joules being emitted per second from the light bulb. So when we talk about stars, we're talking about the total amount of light being emitted per second at the surface of that star, and we call this luminosity. Now let's look at flux. Flux is a measure of the flow of energy onto or through a surface. Let's first look through a surface. Well, remember our analogy of the light bulb? Remember, luminosity is the total amount of energy radiated 1 second at the surface of the light bulb. For a 100 watt light bulb, we're releasing 100 joules of energy per second at the surface of the light bulb. Well, the flux is a measure of the flow of energy through a surface. So let's look at a 1-inch square on the surface of this light bulb. So we have a square that we drew on the light bulb that is 1 inch wide by 1 inch wide. So it's a 1-inch square. And what we want to know is how much energy is flowing out of this 1-inch square on the surface of the light bulb. This would be called flux. So flux is given the letter F, and it is the luminosity per unit area, which in this case would be 100 watts that is passing through 1 inch square. So our flux would be 100 watts per square inches. We could do the same thing for the sun. It's a star, so we want to know what is the flux. In this particular case, we want to know what is the luminosity at the surface of the sun, and we want to know how much of that is passing through 1 inch square. Well, the flux would be the total luminosity of the sun divided by 1 inch square. So this is what we mean by a measure of flow of energy through a surface. Now let's go look at a measure of the flow of energy onto a surface. So here we have drawn a wall, and let's say the distance between the 100 watt light bulb and the wall is 1 meter. Think of a meter stick. So 1 meter is about 3 1/3 feet. So you have this light bulb that's putting out 100 watts at its surface, and that light bulb is located about 3 feet or just over 3 feet from a wall. So let's look at one little square on the wall, a 1-inch square. So one side is 1 inch and the other side is 1 inch. So we have a 1-inch square. We want to know how much of the light from this light bulb is falling on this 1-inch square of the wall. That is another definition for flux. Now we may have had 100 watts per 1-inch square leave the surface of the light bulb, that flux, but it would not 100 watts per 1 inch square would land on this wall, this little 1 inch square of the wall. So in this case, the flux is not equal to 100 watts per 1 inch square. Actually, much less of this luminosity is going to reach that small, tiny square of the wall. And that's because the light is being emitted in all directions. So only a small portion of it is going to fall on this 1 inch square of the wall. So the flux that actually falls onto the wall is going to be less than 100 watts per square inches. And this is what we mean by a measure of flow of energy onto a surface. So how much of this 100 watts is actually reaching the wall? Because the light is being emitted in a sphere, and the area of a sphere is equal to 4 pi times r squared, where r is the distance between the wall and the light bulb, or 1 meter, then the area is equal to 4 pi times 1 meter squared, or 4 pi meters squared. The flux then is equal to the luminosity, or 100 watts, divided by the area, which is 4 pi meters squared, or 2.54 watts per meter squared. So 100 watts left the surface of the light bulb, but only 2.54 watts would reach a 1 meter square segment of the wall. Now, how would I determine how much of the 100 watts reach a 1 inch square area on the wall? Well, I'd have to figure out how many inches are in 1 meter. So I need to solve for r, which is 1 meter in terms of inches. And in 1 meter, we've got 3.3 feet. And in 1 foot, we've got 12 inches. And so if we multiply the top together and the bottom together, we get 39.6 on the top and we get 1 on the bottom. Now meter cancels with meter and feet cancels with feet. So we're left with only inches on the top. So our answer is 39.6 inches. So the flux would be 100 watts divided by 4 pi times 39.6 inches, and the 39.6 inches is squared. So if you multiply out the top and the bottom, you get 100 divided by 19616 inches squared, which is 0.005 watts per inches squared. So you started out with 100 watts leaving the surface of the light bulb, and what falls on 1 inch square of the wall is 0.005 watts per inches squared, or much, much, much less than what left the surface of the 1 inch square from the surface of the light bulb. As the definition of flux is luminosity divided by 4 pi r squared, and we see this r squared in the denominator of the equation, this is an example of an equation that is an inverse square law. Inverse because the r squared is in the denominator, and square because the r is squared. So this flux is an example of an inverse square law. As you step further and further away from the surface of the light bulb, the flux drops off dramatically.